TestBench Structure, the UVM TestBench Top. What is TestBench Top module? All verification component interfaces and DUT are instantiated in all top-level module called TestBench. It is a static container to hold everything required to be simulated and becomes the root node in the hierarchy. This is usually named TB or TB underscore top, although it can assume any other name. Simulators typically need to know top-level modules so that it can analyze components with the top module and elaborate the design hierarchy. Yes, TestBench top example. The example below details the element inside the top module TB top like this. Note the following. TB underscore top is a module and is a static container to hold everything else. It's required to import to UVM underscore package in order to use UVM construct in this module. Clock is generated in the test bench and passed to the interface handler DUT underscore IF1. The interface is set as an object in UVM underscore config underscore DB via set and will be retrieved in the test class using get method. The test is invoked by run underscore test method which accepts name of the test class base test as an argument. Core waveform dump asked if required. Clock generation. A real design may have digital clock blocks that operate on multiple clock frequencies and hence the test bench would need to generate multiple clocks and provide as an input to the design. Hence, clock generation may not be as simple as an average block shown in the example above. In order to test different functionality of the design, many clock parameters such as frequency, duty cycle, and phase may need to be dynamically updated, and the test bench would need infrastructure to support such dynamic operations. The approach shown above may not be scalable and need to be driven from the test bench using hierarchical signal paths since they are instantiated as a module. A better UVM alternative is to create an agent for the clock so that it can be easily controlled from sequence and test using agent configuration object. The reset generation. In a similar way, a reset agent can be developed to handle all reset requests. In many systems, there are two kinds of reset, hardware and software. A software reset is typically done through a register model and will be separated from a reset agent. Hardware reset, including assertion of the system reset pin for a given duration or follow a certain sequence of events before the actual reset is applied. Or such scenarios can be handled separately using this reset agent which needs to handle to the reset interface. Creation of internal tap points. Some test-bench components may rely on tapping internal net in the design to either force or sample values to test certain features. These internal nets may need to be assigned to different values based on an input stimuli and can be done so in the top level test-bench module. Such signals be computed to compute a generic interface and be driven from another agent. Yes, next. Thank you. UVM test. UVM test. What is test case? A test case is a pattern to check and verify specified features and functionality of a design. A verification still a plan lists all the features and other function items that need to be verified, and then the test needed to cover each of them. A different of the test, a lot of different tests, hundred or even more, are typically required to verify complex design. Instead of writing the same code for different test cases, we put the entire test bench into a container code on environment and use the same environment with different configuration for each test. Each test case can override and tweak node, enable and disable agent, change variable values in the configuration table, and run different sequence on many sequencers in the verification environment. So, steps to write a UVM test. 1. Create a custom class inherited from UVM test. Register it with factory and core function new. And 2. Declare other environment and verification component and build them. 3. Into UVM topology if required. And 4. Start a virtual sequence. Okay, next, how to run UVM test. A test is usually starts with TestBench top by a test called run_test. This global task should be applied with the name of user-defined UVM test that needs to be started. If the argument to run test is blanking, it is necessary to specify the test name via a command line option to the simulate using plus UVM_test name. Definition for run test is given below. So now how to run an UVM test. This method is preferred because it allows more flexibility to choose different tests with a modifying test bench top every time you want to run a different test. And also avoid the need for a recompilation since content of the file is not updated. If plus UVM_test name is specified, the UVM factory creates a component of the given test type and starts each phase mechanism. If the specified test is not found or not created by the factory, then a failure error occurs. If no test is specified by command line and argument to the run_test, task is blank, and then all the components constructed before the core to run will be cycled through their simulation phases. The UVM-based test example. In the following example, a custom test called base_test that inherits from the UVM test is declared and registered with the factory. The test bench environment component called m_top_env and each configuration object is created during the build phase and set up according to the needs of the test. It is then placed into configuration database using uvm_configuration_db so that other test bench component within this environment can access the object and configure subcomponent accordingly. And the UVM topology task print_topology displayed all instantiated component and the environment and help in the debug and to identify if any component got left off. A test sequence object is built and started on the environment virtual sequencer using its start method. Derivative test. A base test helps in the setup of all basic environment parameters and configuration that can be overridden by derivative test, since there is no definition for build phase and other phases that are defined differently in dv underscore wr underscore rd underscore register. Each object will inherently call its parent build underscore phase and other phases because of inheritance. Function new is required in all cases, and simulation will give an error message if it's not found. So in this case, only learn underscore phase will be overridden with a new definition in derived test, and each super call will invoke underscore learn phase of the base test. Assume that we now want to run the same sequence as in dv underscore wr our register underscore test, but instead want this test to be run on a different configuration of the environment. In this case, we can have another derivative test of a previous state class and define its build underscore phase in a different way, like that. Thank you. Let's go next. UVM environment. UVM environment. What is UVM environment? A UVM environment contains multiple reusable verification components and defines their default configuration as required by the application. For example, a UVM environment may have multiple agents for different interfaces, uncommon scoreboard, a functional coverage collector, and additional checkers. It may also contain other smaller environment that has been verified at block level and now integrated into a subsystem. This allows certain components and sequences used in block level verification to be used in system level verification. Why shouldn't verification component be placed directly in test class? It is technically possible to instantiate agents and scoreboards directly in a user-defined UVM test class, but it is not recommended to do it this way because of the following drawbacks. Tests are not reusable because they rely on a specific environment structure. Test writer would need to know how to configure the environment, and changes to topology will require updating of multiple test files and take a lot of time. Hence, it is always recommended to build the TestBench class from UVM_env, which then be instantiated with the multiple tests. This will allow changes in the environment topology to reflect it in all the tests. Moreover, the environment should have a knob to configure, enable or disable different verification components for desired task. UVM-env is the base class for hierarchical containers of the other components that make up a complete environment. It can be reused as a subcomponent in a large environment or even as a standalone verification environment that can that can instantiate it directly in various tests. The steps to create a UVM environment. Create a custom class inherited from UVM EMB, register with factory, and call new. Class my call new. And second, declare a build verification component and connect the verification component together. The UVM environment example. This environment has two agents and three sub-environments and a scoreboard as represented in the block diagram shown above. And note that the EMV underscore analog or EMV register environment can have other nested environment and agent within. You can see how powerful UVM becomes in terms of reusability because of this hierarchy structure and TLM interface with each component. Examples in Code Hub. In our code example and following sessions of the basic series, we'll look at a simple test bench structure which instantiated a single agent and a scoreboard as shown in the block diagram below. So, the testament structure translated the following code. Note that the analysis port of the monitor is connected to the export of the scoreboard in connect_phase method. The environment reuse example. Let's assume a DMA controller in SoC has already seen separated verified and standalone unit with its own verification environment when the DMA controller design is used in multiple SoCs in different configurations. The verification environment can also be used in different system-level test benches with multiple configurations. Like that. Okay, thank you. Next is driver. UVM driver. What is driver? UVM driver is an active entity that has knowledge on how to drive signals to a particular interface of the design. For example, in order to drive a bus protocol like APB, UVM driver defines how the signal should be timed so that the target protocol becomes valid. All driver classes should be extended from UVM_driver, either directly or indirectly. Transaction level objects are obtained from the sequencer, and the UVM driver drives them to the design via an interface handler. Steps to create a UVM driver. Create custom driver class inherited from UVM_driver. Register with factory and core new. Declared virtual interface handle and get them in build phase. Code the run_phase. The UVM driver sequencer handshake. UVM driver is parameterized class which can drive a specific type of transaction object. The driver has a TLM port of type UVM underscore SEQ underscore item underscore pull underscore port, which can accept the parameterized request object from the UVM sequencer. It can also provide a response object back to the sequencer, and usually the class type of both request and response items are at the same. However, they can be different if explicitly specified. So the UVM driver uses the following method to interact with the sequencer. Method name get underscore next underscore item description blocks until a cast item is available from the sequencer. This should be followed by item underscore done call to a complete handshake. Next, try underscore next underscore item. Non-blocking method which will return null if a request object is available from the sequencer, else it returns a pointer to the object. Item done. Non-blocking method which completes the driver sequencer handshake. This should be called after get underscore next underscore item or a successful try next item call. Then, how a driver a sequencer API methods used. The idea behind the driver sequencer handshake mechanism is to allow the driver to get a series of transaction objects from the sequence and response back to the sequence after it has finished driving the given items so that it can get the next item, right? So first, get underscore next underscore item followed by item done. This use model allows the driver to get an object from the sequence. The driver drive the item and then finish the handshake with the sequence by calling item underscore done function or task. This is the preferred use model since the driver need to operate only when the sequencer has an object for the driver. Here, finish underscore item calling the sequence finishes only after the driver returns item underscore done call. The second, the two, get followed by put. The difference between this model and the previous one is that here, the driver gets the next item and sends back the sequence handshake in one go before the UVM driver processes the items. Later, the driver uses the put method to indicate the item has been finished. So, finish underscore item call in the sequence as finished as soon as get is done. The UVM driver example. Note the following from the example shown above. Driver is extended from UVM underscore driver. Virtual interface handler VIF is declared and assigned later in the build phase. Real interface object is retrieved from the database directly into a local variable using UVM underscore config underscore db ::get method. Get the next data item from sequencer using seq underscore item underscore port dot get underscore next underscore item in run phase. Can a core drive task to send data in accordance with the protocol. Indicate to the sequencer that the data item has been driven using sequence underscore item underscore port dot item underscore done. The other details, the base driver class contain a UVM under seq item per port through which can request for a new transaction from the export connected to it. The ports are typically connected to the export of a sequencer component at the parent class where the two are instantiated. The RSP port needs connecting only if the driver will use it to drive it write responses to the analysis export and the sequencer. The driver's port and the sequencer export are connected during the connect phase of an environment agent class. Thank you. See you next. Sequencer. Sequencer. A sequencer generates data transactions as a class object and sends it to the driver for execution. It is recommended to extend UVM sequencer UVM underscore sequencer base class since it contains all of the functionality required to allow a sequence to communicate with a driver. The base driver base class is parameterized by the request and response item types that can be handled by the sequencer. Usage. By default, the response type is the same as the request type, and if required to be different, you may specify it as a second parameter during instantiating. Unless you have additional port to be included, you should directly instantiate it as a UVM underscore sequencer, parameterized to the required data item. Generation of object with the sequencer is very limited in terms of flexibility and reusability. We will see how this limitation can be overcome via sequences. Custom sequencer. And it's not really required to create a custom sequencer to execute every sequence or for every agent, but you can create your version of a UVM sequencer with additional features and create instances of it throughout the test bench. Class hierarchy and refer to class definition for UVM sequencer method declaration. Thank you. See you next to UVM sequence. What is a UVM sequence? The UVM sequence is made up of the several data items which can be put together in different ways to create interesting scenarios. They are executed by an assigned sequencer which sends data items to the driver. Hence, sequences make up the core stimuli of any verification plan. Steps to create a UVM sequence. Create a user-defined class inherited from the UVM underscore sequence, register with factory, and call new. Second, declare the default sequencer to execute this sequence. 3. Define the body method. The UVM sequence example. Note the following from the example shown above. My underscore sequence is inherited from UVM underscore sequence. It's registered with the factory using backward UVM underscore object underscore utils because it's a transaction item. The main stimulus is written within the body task, while pre-body and post-body are useful callbacks to be used if required. And a data packet is created and sent for execution using uv_do macro. Pre-body and post-body methods are not invoked in a backward uv_do macro call. The uv_do macro will allocate an object of a type myData to pkt, randomize it, and send it to the default sequencer associated with to execute this sequence. Use of this macro simply reduces the code required to achieve the objectives mentioned before. Now, the next section. Next is monitor. UVM monitor. What is monitor? A UVM monitor is responsible for capturing signal activity from the design interface and translate it into a transaction level data object that can be sent to the other component. In order to do so, it requires the following. A virtual interface handle to the actual interface that its monitor is trying to monitor. TLM analysis supports declaration to broadcast captured data to others. What does a UV monitor do? A UV monitor is derived from UV monitor base class and should have the following functions. Collect bus or signal information through a virtual interface. Collected data can be used for protocol checking and coverage. Collected data is exported via an analysis port. The UV monitor functionality should be limited to basic monitoring that is always required. It may have knobs to enable, disable basic protocol checking and coverage collection. However, function checking should be done outside the monitor in a scoreboard. Steps to create a UVM monitor. Create a custom class inherited from UVM monitor, register with factory and call new. Second, declare analysis port and virtual interface handlers. Functions and tasks in a class are recommended to be declared as virtual to enable child classes to override them. Click 3D polymorphism. And third, build the UV monitor and code the run phase. So, the UV monitor example. Note that following from the example above. Monitor is extended from UVM_monitor. Virtual interface handle is declared as VIF and assigned to the UVM database via UVM config db get method. Additional knobs are provided for enabling, disabling protocol checker, enable_check, and coverage, enable_coverage. Coverage group defined as CG trends and it will be samples during run phase. During run phase, data from interface is captured into local class object. Protocol check is performed when the enable and coverage group is sampled when enabled. Data object class is broadcasted to other verification components via the analysis port. The knobs can be disabled the task by using UVM's database. The recommended practice. UVM underscore class should be used as a base class for user-defined monitors so that it allows you to distinguish monitor from other component types also using its inheritance. Any future changes and addition to the UVM-based UVM monitor class will be automatically included in your derived class. Thank you. See you next section. Agent. UVM agent. What is a UVM agent? An agent encapsulates a sequencer, driver, and monitor into a single entity by instantiating and connecting the components together via TLM interface. Since UVM is all about configurability, an agent can also have configuration options like the type of UVM agent, active and passive, knobs to turn on features such as functional coverage and other similar parameters. What are all types of agent? Active. Instantiated all three component sequencer, driver, monitor enables data to be driven to DUT via driver. Passive. Only instantiating the monitor. Used for checking and coverage only. Useful when there's no data items to be driven to DUT. So, how to find out a UVM agent is active or passive? User-defined agent class drive the UVM agent also have another function called getAsActive, which will return the state of request to UVM agent. Steps to create a UVM agent. Create a custom class inherited from the UVM underscore agent, register with refactory and call new. An instantiated agent component. And instantiate and build the component. Connected for the connect agent components together. What does a UVM agent do? Usually, it makes sense to create an agent that provide a protocol-specific tasks to generate the transaction, check the result, and perform coverage. For example, a UVM agent can be created for visual protocol whose sequencer will generate data items which can be sent to the driver. The driver then converts the data item class object into actual pin level signals and drive them to the DUT. The monitor may passively collect the output of the DUT, convert them back into another data item class object and distribute it among the component and the test bench waiting for the items. How to configure a UVM agent as a passive or as passive or active or passive. A user-defined agent derived from the UVM agent has an internal variable called isActive, which is of enum type, UVM active passive enum. By default, all agents are active. So, example of an UVM agent. Each agent should have a configuration object which will contain a reference to the virtual interface that can be used by the driver and monitor to access pin level signals. This object can be contain other data members, which will control which of the agent subcomponents are built, and it may also contain information that affect the behavior of the agent components. Some of the other functionality that can be included are functional coverage monitor to collect protocol interface information, and scoreboard if required to be checked the protocol data, API sequences that might be useful for implementing an API layer. Note the following. An agent should be derived from the UVM class UVM agent. Agent being a component is registered with the factory using macro UVM component utils. Instantiated M SCQR0, M driver0, M MON0 are sequencer, driver, and monitor respectively. UVM passive active and passive enum is a UVM enum declaration that stores UVM underscore active or a UVM passive. This is usually used to configure the agent to be either active passive, and the build phase sequencer and driver are created only if the agent is configured to be active. The variable is active can be set either at the environment level via configuration object retrieved from resources database. Similarly, connection between sequencer and driver needs to be done only if they were built during the build phase. The recommended practice: it is recommended to drive your own agent from the base class UVM agent for the following reasons: allows you to distinguish agent from other component types also using its inheritance, and any future changes addition to the UVM agent class will be automatically included in your derived class. Has each get is active method which will return the state of the agent. Thank you. See you at the next section. Scoreboard. UVM scoreboard. What is scoreboard? UVM scoreboard is a verification component that contains the checkers and verify the functionality of a design. It usually receives a transition level object captured from the interfaces of a DUT via TLM analysis ports. For example, write and read value from the RW register should match. When a write operation is performed to the design, the scoreboard receives this packet and the respective value. After that, the same value is read back from the design and the data is actual value which is sent to UVM scoreboard. Now the scoreboard can compare between the expected and the actual values to see if they match. What is your reference model? After receiving data object, it can either perform pre-calculations and prediction the expected value, or it do the reference model to get expected values. The reference model is also called a predictor and would mimic the functionality of the design. The final task is compare expected result with the actual output data from DUT. It's recommended to inherit from the UVM underscore then the UVM component so that any addition to the UVM scoreboard class in the future release of the UVM will automatically be included in the custom UVM scoreboard when you switch it to the newer version. Steps to create a UVM scoreboard. First, create a custom class inherited from UVM underscore board. Register with the factory and the call function U. 2. Add a necessary TLM export to receive transactions from other components and instantiate them in the build phase. 3. Define the action to be taken when the data is received from the analysis port. 4. Perform checks. It's not required to perform checks only in the check phase. Real checkers can also actively check during the run phase. The connect analysis port of a scoreboard with the other component in the environment. The other components in the test bench send data to the scoreboard via analysis port by calling the port write method. For example, a monitor collects data packet from the bus interface. The packet is complete when the bus operation has received or sent all the data associated with the transfer. The monitor calls the write method or its analysis port after formulating a complete package. The scoreboard will get the data packet, send the analysis port of the monitor, and the scoreboard are connected in the environment. The UVM score example. My underscore scoreboard is a class inherited from UVM scoreboard board and registered with the factory. A UVM analysis implementation port called AP underscore IMP is defined to accept the transaction of the of type APB underscore PKT UVM underscore sequence item. Because AP imp is also a class, an object has to be created using the new method, which able, which which been which has been done in the build phase. The implementation of the analysis port is only complete when we define the right method to handle the incoming packet appropriate. And how to connect the analysis port of the UVM scoreboard. After scoreboard has been defined, you also need to instantiate it in the environment and connect it with the appropriate analysis port. Okay, see and next this section. Subscriber. Subscribers are basically listener of an analysis port. They subscribe to a broadcaster and a receive object whenever an item is broadcasted via the connected analysis port. A UVM underscore or UVM component class doesn't have an inbuilt analysis port, while a UVM subscriber is the standard version of analysis port named analysis export. Class definition. Use class. In a typical case, an agent would have a TLM analysis port for each monitor to share the data object it collected on the agent interface with the other test bench component. So it is easier to create a user class inherited from the UVM subscriber and use the inbuilt analysis expert implementation to connect to the analysis port of the agent. For example, you could have functional coverage groups and cover point in a subscriber and have them sampled whenever and receive an object from the agent. So it is not mandatory to inherit from the subscriber, but is recommended practice so that there exists a uniform way through which a component can connect with an analysis port. Thank you. See in the next section. The UVM virtual sequencer. In simple terms, it is a UVM sequencer that contains handles to other sequencers. Why do we need this? Because we plan to use virtual sequences and wanted to have a control over the all sequencer from the central place. A request type is not for required here because the sequencer is generic and not limited to handle only one particular data type. Click to refresh the concept of virtual sequence. The environment shown above has an APB agent, receiver agent, PCI environment, and a register layer environment. Each of these components have each on their own sequences and a respective sequencer on which they are launched. A virtual sequencer called m underscore virtual underscore sequencer is instantiated to hold references to each individual sequencer. Hence, a virtual sequence executing on this virtual sequencer will have access to all sequencer in the test bench. Example: in our top environment, we'll create an instance of a virtual sequencer and connect the real sequencer with their respective handlers in virtual sequencer. And virtual sequencer operate best when used with a virtual sequence. Read more on virtual sequence. Go to the download page, example code under tag virtual sequencer. Thank you. See you on next chapter.